Regular expressions are powerful patterns used for matching character combinations within strings. They constitute a small, specialized language that is integrated into JavaScript and many other programming languages. In this example, we are creating a pattern, hello space world, using forward slashes. The I at the end indicates case-insensitive matching. We then define a text string, hello world. The test method is used to check if the pattern exists in the text. The output of the test method is a Boolean value, true in this case since the text contains hello world, irrespective of the case. Thus, it demonstrates the basic usage of regular expressions in JavaScript. Regular expressions use special characters called metacharacters to define patterns. A dot matches any character except a new line. A caret matches the beginning of the string. A $sign matches the end of the string. \d matches any digit from 0 to 9. \w matches any word character, including uppercase A to uppercase C, lowercase a to lowercase c, digits from 0 to 9 and underscore. \s matches any whitespace character like space, tab, newline, etc. These metacharacters are building blocks for creating patterns. In the code example, hello, \d plus matches if the text starts with hello, followed by one or more digits. World followed by dot and dollar matches if the text ends with world, followed by any single character. \w plus, \s, \w plus checks if the text contains a word, followed by a space, followed by another word. Quantifiers specify how many times a character or a group should appear in a string. An asterisk means 0 or more times. A plus sign means 1 or more times. A question mark means 0 or 1 time. Curly braces with a number inside means exactly that many times. Curly braces with two numbers n and m, separated by comma means from n to m times. Curly braces with a number followed by a comma means that number or more times. Character classes, on the other hand, are used to define a set of characters. Square brackets with O inside matches any vowel. Square brackets with caret and 0 to 9 inside matches any character that is not a digit. Square brackets with A to Z inside matches any uppercase letter. In the code example, \d plus matches one or more digits. \d in curly braces, 2, 4, matches 2 to 4 digits, and \w in curly braces 3 followed by O matches 3 word characters followed by O. Capturing groups are a way to treat multiple characters as a single unit. These groups can later be referenced for further use. A pattern enclosed in parentheses creates a basic capturing group. A pattern enclosed in parentheses followed by $:, is a non-capturing group that does not save the captured value. A pattern enclosed in parentheses followed by $, name, allows capturing groups with a name. \1, \2, \3, etc. are backreferences to the captured groups. In the code example, we are defining a regular expression that matches an email pattern with 3 capturing groups. The first group captures the username. The second group captures the domain name, and the third group captures the top-level domain. The match method returns an array. The first element of the array is the full match, and the subsequent elements of the array are the capturing groups. Lookahead and lookbehind are called assertions. They check for the presence of a pattern ahead or behind the current position without including them in the match. $= followed by a pattern is a positive lookahead that asserts that the pattern exists ahead. $! followed by pattern is a negative lookahead that asserts that the pattern does not exist ahead. $<= followed by pattern is a positive lookbehind that asserts that the pattern exists behind. $! followed by pattern is a negative lookbehind that asserts that pattern does not exist behind. In the example, a complex password validation regex is defined that ensures that the password contains at least one uppercase letter, at least one digit, at least one special character, and at least 6 characters using positive lookaheads. Named capturing groups allow you to refer to groups by names instead of numbers, which enhances the readability and maintainability of regular expressions. In the URL parser example, we have named groups protocol, domain, and path that stores the respective values from the URL. These values can be extracted by referring to their group names. Backreferences, on the other hand, allows to refer to a previously captured group within the same regular expression. \1 refers to the first capturing group and so on. In the examples given, \b, \w+, \s+, \1, \b checks for repeated words in a string. The second example shows a simple HTML tag matcher, and the third example shows a named backreference for matching HTML tags. JavaScript provides several built-in methods that can be used along with regular expressions for performing various operations. The match method returns an array of the matching results. The matchAll method returns an iterator of all the matches. The replace method replaces the matches with a new substring. The split method splits the string by the provided pattern. The search method returns the index of the first match. In the example, match method, when applied to a string Hello World 2024, with regular expression \d+, gives the array with one element 2024. The replace method, when used with the same string, replaces the match 2024 with 2025. The split method splits the string by whitespace and returns an array. Finally, the search method returns the index of the first occurrence of world in the string, which is 6. Regular expressions are often used for data validation, and there are standard patterns used for common use cases. The email pattern matches email addresses. The phone number pattern matches US phone numbers. The URL pattern matches URLs starting with HTTP or HTTPS. The date pattern matches dates in the YYYYMMDD format. In the code example, the email pattern is tested against a valid email and returns true. Similarly, the phone number pattern is tested against a US phone number and returns true. Optimizing regular expressions can significantly improve performance. Start with anchors, which are the caret and the dollar symbols, to avoid unnecessary scanning of the string. Avoid greedy quantifiers like asterisk and plus. Prefer lazy quantifiers like question mark whenever possible. Be specific by using character classes instead of dot. Cache the regular expression objects to avoid creating regular expressions in loops. In the code example, the first regular expression is greedy and unanchored, which makes it slow. The second regular expression is specific and anchored, making it faster. In the loop example, the regex is created in each iteration, making it slower. The cached regex example avoids recreating regular expression objects, thus making it more efficient. When working with regular expressions, it's important to follow best practices and avoid common pitfalls. Always test with edge cases, such as empty strings, special characters, and boundary values. Break complex patterns into smaller, more manageable parts to enhance readability and maintainability. Use verbose mode using the X flag to write complex regular expressions with comments for better understanding. Some common pitfalls are overusing wildcards like .*, which makes the regex slow, and forgetting to escape special characters. For example, a dot matches any character. To match an actual dot, it should be escaped with a \. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.